Hi everyone, this is Beroz, and today I'm walking you through one of the most important position papers in modern machine learning, which is a landmark paper in causality, which is called towards Causal Representation Learning by Bernard et al. And it was published in IEEE Proceedings in 2021. And the main topic of the paper is decoupling the entanglement that has happened and why causal representation learning is inevitable in AI. So the illusion of IID intelligence is the first point that was talked in the paper is that look at the contrast here. A crow can take what it learned in one situation and can apply it to a completely new problem. That's called strong generalization and natural intelligence. Modern machine learning cannot do that. It only generalizes from one point to the next when both come from the same distribution. That's called IID, independent and identically distributed. But current deep learning treats real world phenomena like domain shifts, interventions, and changes over time as a new nuisance, something that engineer something to engineer away with bigger data sets. The authors argue this is a fundamental design flaw. The moment that the test distribution differs from training, even slightly, these models fail catastrophically. So, the animals and humans don't have this problem. The question is why? So the limit of statistical correlation. Here's the core distinction in one image. On the left, you can see the probability of y given x. If you force every umbrella in the city closed, uh, uh, seeing open umbrellas is a strong predictor of rain. As statistical learning is fine with this, but on the right, the probability of y given you do intervention on x or you changes x, an active intervention, if you force every umbrella in the city closed, will the rain stop? Obviously not. But a purely statistical model has no way of knowing that. It only sees correlation. So this is a wall machine learning keeps hitting again and again. Prediction is fixed. In fixed condition is solved. Prediction under action, under intervention is not. And nearly every real decision a system makes in a real world is an intervention. So now if we come to the taxonomy of reality, so this table is the spine of the paper, which I have came to know is that it tells about four models. A full physics model can do everything, but you can't learn it from data. You need a human expert. A purely statistical model learns from data easily, but breaks the moment the distribution shifts. The highlighted row, the structural causal model, SCMs, is a sweet spot. It can predict under distribution shift, answer counterfactuals, and we learn from data. This is where the field is heading. So, breaking the entanglement is the important concept. So, a famous example in Europe, the frequency of the storks correlates with human birth rates. Three graphs explain this equally well. Stork causes babies, babies causes storks, or some hidden third variable like economic development. It causes both. The Reinbach's principle says when x and y are statistically dependent, something is causing it, but observational data alone, no matter how much of it, cannot tell you which of these three structure is the truth. The statistical signal is identical in all three cases. This is the key takeaway. A causal model contains genuinely more information than a statistical model, and you cannot get there with more data alone. Now, the mathematics of autonomy. There are many ways to factor a joint distribution. The top equation is one valid factorization, a chain rule expansion, in which is mathematically correct, but the pieces are entangled in reality. Change one physical mechanism in the world, and every term in the product changes. But the bottom equation, which is causal factorization, each variable is written as a function of its own direct parents in the graph, plus an independent noise term. This factorization isn't just mathematically valid, but it mirrors the actual physical mechanisms that are generating the data. That difference is everything. The statistical factorization tangles them together. The independent mechanisms principle. This is the central principle of the paper. The world is composed of autonomous modules, like independent knobs and dials. They don't talk to each other. It has two parts: influence, independence. So, what it is that turning the light knob does not change the object shape mechanism. They cannot be intervened on separately. Information independence. What is information independence? If I show you one mechanism, it tells you nothing about the other. Knowing how lighting works give you zero head start on understanding the object shape. This is what makes knowledge transferable. If mechanisms are truly independent, you can learn one once and reuse it everywhere. The sparse mechanism shift, SMS. So this is the most actionable hypothesis in the paper. Watch what happens when a finger pushes a cube and the cube falls. In the pixel space, the top image and the bottom one is the what happens in reality. So in the top image, every pixel changes. Hundred of features shift simultaneously. The change looks dense and chaotic. But in the latent causal space, the bottom one, which is also real, only one or two variables change: the finger position, the cube position, that's it. The intervention is sparse. The hypothesis is that real world distribution changes almost always look like this. They affect a small number of mechanisms locally, not all of them at once. If your representation has the right structure, change becomes simple. If it doesn't, change look like chaos. This is the strongest practical bias for learning good representation. The missing link, raw data to causal nodes. Here's the gap that paper names. Classical causal inference assumes the variables are already given. The temperature, the blood pressure, GDP, a human expert hands them to the algorithm. But raw data, pixels, audio waveforms, sensor streams has no such structure. They are no labeled nodes. The whole point of causal representation learning is to bridge this gap, discover the high level causal variables directly from the low level observations without humans labeling them. This is where deep learning meets graphical causality. Now, extracting the architecture of reality. So here's the proposed architecture in the paper. Raw input on the left, a robotic scene with cubes, a neural network encodes it into a small set of latent variables S1 through Sn. These are intended to be the actual causal variables that we discussed earlier: the finger position, cube identity, and cube position, because each module reflects a real physical mechanism, and the same module can be reused across many downstream tasks without retraining. That's the payoff: one representation, many tasks, compositional, transferable, modular. The directionality matrix. So this is very important to also know that uh, a familiar machine learning, this comes to the famous machine learning technique. When you predict effect from cause, on the left side, the input distribution, the probability of x and the conditional probability of y given x are independent modules. So unlabeled data tells us about x, tells x tells you about nothing about the conditional setting. So semi-supervised learning is theoretically impossible here. But when you predict cause from effect, like classifying a digit from an image where a label generates the pixels, the input distribution does contain information about the conditional aspects. So semi-supervised learning works, which is shown on the right. So the empirical result holds. Tasks where SSL succeeds are overwhelmingly anti-causal. Tasks where it fails are causal. This is the kind of thing causal thinking lets you predict in advance instead of finding out the hard way. Adversarial robustness via causal transfer. A stop sign with interceptable pixel noise. The statistical classifier reads it at a 60 mph speed limit. It learned the label from pixel level statistical artifacts that have nothing to do with what physically makes stop sign a stop sign. A causal classifier, on the other hand, ignores those pixels chaoticness because they don't structurally cause the label. The shape, the octagon, the letters, those are the causal features. Adversarial attacks exploit the fact that current classifiers don't know the difference. Causal representations close that gap by design. So acting in the imagined space. So this is the link to the reinforcement learning. A causal world model lets an agent simulate consequences without acting in real world environment. The counterfactual reasoning, what if I had taken a different action or a different route to the class? A famous example by our professor, that's why I'm quoting it. Lets it learn from a fixed log of past data without new experiments. This is exactly what offline reinforcement learning needs, and it matches what cognitive science calls Lorentzian intelligence. Thinking is acting in an imagined space. Without a causal model, an agent has no imagined space to act in. Approximating the causal graph. So here's the sharp reframing of the paper. The three of the most successful trick in machine modern deep learning, data augmentation, self-supervised learning, massive pre-training, all are crude approximation of causal intervention. Augmentation simulates spatial intervention. Self-supervision forces the model to extract invariant features. Pre-training maximizes the exposure to variant environment. They work, but they are patchy and ad hoc. The paper claim is that an explicit causal framework optimizing worst case out of distribution risk would unify these tricks under one rigorous mathematical objective. So the last point of the paper is that from pattern recognition to general intelligence, three calls to action that summarizes the entire paper in my understanding. Number one is that stop treating distribution shifts as enemies. Use them as supervision signals to discover the causal structure. Number two, stop building monolithic networks. Build modular ones based on independent causal mechanisms. Number three, stop optimizing only for in distribution accuracy. Optimize for robustness to interventions. And the IID pattern recognition is a mathematical abstraction. Causality is the bridge to versatile autonomous AI. So that is all from my side. Thank you and for your attention.